trade-off. It's very simple. If you see everything as false, in this point you get 100% right, but in this place you get 100% wrong, because that's the probability of the class. And the okay, no, this is not this is ours. Let me do it that way. False positive and true positive. If you claim everything is positive, so what? You got it here. Everything is 100%, 100% for true positive, 100% for true negative, for false positive. Your precision is very low. Your precision is very low. You can say everything positive, your precision is what? Who knows? Depends on what it is. It's the baseline, right? But on the other hand, if you say everything is negative, your precision is 100%, but your recall rate is 0. So this trade-off is the same trade-off between the recall and the precision here. So sometimes you have one scheme, it look like this, another scheme look like this. If you use the what I call boost, the ensemble method, you merge the two together, like what? It's not a bag, boost stack. No, boost stacking method. 1 2 combined together, and to learn, you can make anywhere between this convex hole. Means any line in this region is okay. It's your kind of trade-off between these two schemes. So the formula is this. And one scheme, true positive, false positive rate is here, true positive, false positive. Another one is this. And if you merge the two, you can redistribute the weight, give which one more credit. And then you can end up this is your merged combined rate. You remember the last example I talked about the eta boost? That's exactly how we do it. The 3 numbers, you first one get a 3 mistake in the end, another get a 3 mistake in the middle, another get a 3 mistake in the beginning, and you get it right away, you can get it very nice. And a similar idea, just want to minimize the cost. So the lift chart comes from the marketing. You just remember this plateau theorem, and the 20%, 80% always come from signal processing. It's the false alarm and the true positive. You know, it's kind of where you set up the best threshold, and then they're going to minimize the noise but get most of the signal. And always that's the issue. And then the recall precision comes from the natural language process and the information retrieval. They're very close, actually. Now, put all together, the best way, the mathematicians always need to measure. You just use the curve to see which one is better than the other. It depends on the weight function. And this U, not always 1, 1, 1. You need to put the weight of the cost. That's a few scheme. In that case, if you always say negative in the beginning, because you always say negative in here, you have 0 error. In the here, you get 100% of error, because this line has the error. Now understand this line. Without understanding this line, you cannot read this line. That's the probability of your class, whatever class is. You could be, if the probability is 0, you say 0, you don't have any error, right? If the probability is 0, you say 20%. That's the 20% of the false positive, right? Because there's no chance why you say positive, right? Okay. And if I give you, this is all male, how many have given birth? Well, of course, probability is 0, you say 20%. That's all you are false positive. error. Are you with me? And this other side, you have 100% partial probabilities, right? And then if anything you say the no, that's the error. That's the false negative, right? If I got this 100 women, I said how many of 100 mothers in the nursery home, and I said how many have babies? That's 100. You said 80%. Then your false negative is going to be the error, right? That's the two extreme. In the between, that's the line. The arrow is really an addition between this false positive and the false negative. Depends on uniform weight, then this is straight line. Uniform weight is a straight line. The two extreme cases tell you something. If you always say no, see, when the probability increase, you still say no, that of course down. Your error started rocked up, right? But on the other hand, if you always say yes, in the beginning, there's no chance to say yes, you say yes, your error is 1, and all the way, if it's 100% yes, then you say, that's this line. A little easy scheme, like a naive Bayesian. In here, you cut a line. In this line, you say yes, no. In here, you say yes, then your error is this triangle shape, right? Make sense? So, if it's uniform cost, you look at the line, you can compare which one is better for what circumstance, what probability. You can look at the adaptive, kind of classify based on the probability and the cost line. That adaptive is if in the baseline, I always look at this B line, which have the same amount cost to the false positive and the false negative. That baseline means if the false negative is 10 times more than the false positive, in order to get this even line, you need to get 10 times of the false positive, right? Then you get the even cost. That's let's say the even cost of 1/4. That's the cost line. But you see, that's the line I'm talking about, naive Bayesian. Before 50%, you always say no. That goes up to 50% of error, right? Right. After 50%, you always say yes. You get this line, right? And then you see 50%. But you can also improve. If you have 3, you choose. You can always choose to here. Always say no. That's your threshold. And then here, yes or no. You even split it like based on the cost. Go to that line. In here, you always say yes. Can you see? That's improvement, right? Like the boost. But however, you can keep improving. You can merge a lot of other lines and then adaptive, according to here, the probability start to adjust it. You can always minimize your cost. Again, mathematics, I think the number one use is either minimization or approximation. This is or optimization. Without this, you really equal, never learn the best. Okay, now that function is nothing more than the probability times the penalty function in the column divided by the normalization. The normalized means the penalty based on the false positive, the penalty based on the false negative. But you can root square, and you can do the absolute value. And what's the difference? Well, if you square, look, they have a heavy penalty to the outliers, to the two ends. If it's too extreme, you're going to punish the heavier. For this, you punish the even, right? So it's a kind of how much you want to punish that, what kind of error. Okay. We, in the end, also look at the correlation coefficient. The third one is statistical. And if this is the perfect prediction, that's your model prediction as compared with the perfect benchmark. And the more you are correlated, the better off you are, right? So that's another measurement. The same thing, basically. You just divide by the standard deviation. And here's the cross multiplication. That's the standard deviation of your prediction. That's the standard deviation of the actual class. And then, of course, the more close to 1, the better off you are, right? And the go to 0 is bad. Negative 1 means you just did the completely wrong thing. Well, here is the measurement. 4 different measurements for 4 different classifier A, B, C, D. Most they confirm each other, but there are some in the controversial region. Depends on really what are you looking for, domain specific. So in that case, it is clear D is the best. Why? The correlation is very high to 1. Can you see it? That's a statistical way. And the least square mean is low. It's the smallest one. And also look at the other one is pretty small. That's clear the best. You see? And that's the second clear. And you see, pretty much no controversy. That's a pretty high, consistent with the second best. But these two, you really don't know. It's another principle, like Epicure's principle. It's good to keep them all instead of Occam's razor. You remember Occam's razor? The simple is the best. That's a philosophy. And so is Epicure. He said, why not keep all? Keep them all. That's it. This time, keep them all. So, but you cannot say elegance and then all error. Plenty of error. That's not good and elegant. You need to balance the two costs. A classical example is this. If you look at Copernicus, how do you say Copernicus? Right? Close. Sorry to me. I know the Chinese word. When you have that one, then you cannot ever speak it right. And the latest refinement of Ptolemaic theory of epicycles, that's too complex. And the Kepler made the 3 law really elegant, but have a little more error. That's fine. And one very simple elegant that explains the data most perfectly. But the other one significantly more complicated, but reproduce the data without any mistake. Which one is what you want? Of course, it's the one you want the most elegant. So MDL compression, you look at the, since you need to compute the size of the model, the space needed to encode the error. These two are the penalty. And the first, the space needed to encode the error, that's easier. You use the bits to talk about it. And then all the loss function is the entropy function, right? How do you encode the model in the decision tree? You remember that's how many internal the nodes you have, and you take the logarithm, right? Depends on your class and your attributes and the split. You count how many nodes, take the logarithm. And this decision tree comes this principle that discrete lengths equal the length of the theory and the length of the theory with the error, with the exception, or whatever you see thinking. That's how you add. In the decision tree, that's the arrow, and that's the tree, in the nodes and the leaves. But if you use the naive Bayesian, that's the what you call the condition probability. That you cannot see. There's a probability. I don't know why it's not shown. The probability of when you see all the instance and look at the theory, the condition equals this divided by that. And that's the instance you see, the training data, that's your probability of the theory, the probability of the theory, and then what's the probability of this instance? Come up with this. Take the logarithmic. And if you map this to here, that's how many bits you want to code the arrow, and map this to here as the length to look at the theory, that comes with the same idea.